Okay, so welcome back. This is our 5th lecture in discrete mathematical structures. In the previous 2 lectures, we defined the notion of the proposition in logic. So propositional logic is the area that we're in. What does it mean to be a proposition? And then after that, we learned that we can define propositional equivalences on these declarative statements that are either true or false. And then once we were comfortable with that notion, we moved on to establishing logical identities between propositions, right? And these logical identities were kind of strung together with operators between propositions and formed compound propositional equivalencies. In today's lecture, we're moving towards a more general notion, or maybe more applied notion of these concepts with what are called predicates and quantifiers. Now, the best way to illustrate what a predicate is first, before we move to quantifiers, is probably with a few examples. So like, consider the statement, maybe, I don't know, let's make a declarative statement that depends on something. So consider the statement, x is greater than 3. So that statement does declare something, right? That's this, but depending on the truth value of this side of the statement, not depending on the truth value, depending on the input that we place into the statement, x, this side of the statement is going to determine whether or not it's true or false. So in the statement, the predicate would be, so the right-hand side that does not involve the variable, just to say it out loud before I write it. So the predicate would be is greater than 3. Okay. And the variable would be x. So that's kind of like obvious, I would assume. And I think that this simple example of a statement illustrates what a predicate is. It's the is part of your declarative statement. And the thing that follows the is part is your variable. Now, I typically don't refer to these things as predicates and variables often when I'm talking. I think of them as propositional functions. Whereas like the statement itself is the propositional function, the predicate is the thing that determines its truth value, and the variable is the input to the function. So more or less, this lecture will be about considering propositional functions, where the truth value depends on what we input into the statement. So maybe I'll just write that out. So propositional functions are declarative statements whose truth value depends on a variable. Now, this is not as precise as I would like it to be, because there's another aspect that we'll get to during the lecture that also determines the truth value of something like this, a declarative statement with a variable involved. But maybe to like illustrate that point before we get there, consider the statements there is a student in this class that uses Linux. So that is a declarative statement, but there are some things that are kind of, you know, obviously dependent on this class. And then also, we should probably point out that the variable is not as clear to point out as it is in this statement. Like the x variable for x is greater than 0, obvious. In this declarative statement, the variable is not so, it's not as obvious. Maybe it still is, maybe I'm overthinking it, but I think that it's not as obvious. So in this statement, what? The variable would be what? Student, right? So depending on the student's name that I stick into this declarative statement, I'm assuming that some of you don't use Linux, but maybe one of you does, maybe, okay? So this would be my variable, okay? And then now that I have a variable, that's good to identify and necessary, but there's also another condition that kind of satisfies whether or not this statement will be true. Or maybe not even like determines if it's going to be true, but is like inherent to the statement at question. And that is this part. This class. Now, what this is kind of hinting at, if we're thinking about functions, well, I sort of want you to think about it for a moment. Like when you encounter functions in algebra and pre-cal and calculus and whatever, anytime you encounter a function, it's kind of easy sometimes to forget a really important aspect when looking at functions. And that is the domain, right? In order to really know the behavior of a function, you have to understand the domain of which you're working in. So this class is kind of implying to us that we're talking about Math 2305, section whatever, 4 o'clock on Tuesdays and Thursdays, right? So in propositions, you have to be wary of what is the domain of discourse, okay? So instead of writing domain of discourse for the sake of space, I'll just write, this implies a domain. Right? Again, from the vantage point, or not from the vantage point, but from the mental model that we're building of these things as treating these declarative statements as functions with a variable, which immediately, once you have variables, you have to think about what the domain is anytime you're encountering a function. And I think that maybe I have a good illustration of this. For example, consider the statement the square, or I'll say x squared is greater than or equal to 0. Consider that statement, right? It's declaring something, and we haven't specified anything about the possible choices of x, but just looking at it, if x is a number, some number, right? do you think that that's true? That x squared is greater than or equal to 0? Does it seem to be true? Like 1 squared is, yeah, like 1 squared is 1, -1 squared is +1, 0 squared is 0. It seems like it would be true. However, if we don't specify the domain of interest, and even if we're thinking about numbers, there's a chance it might not be true. For example, what about if x is equal to imaginary I? Right? What if, so I is equal to the square root of -1. In this case, if I choose this as my value of x and I put it into that statement, what happens? That squared is just -1. Oh, -1 is not greater than or equal to 0. It would be false in that case. So understanding that there's a domain of interest is pretty important for this, for these types of things. Understanding domain is important in all of like dealing with functions, right? And these weird oddities do occur, especially when you're dealing with interesting things. I think it's kind of, it can be annoying for students, but it also makes the subject of mathematics interesting to some people, in that the examples that you see in a lot of textbooks or the things that you're assigned, you see on exams, are kind of like cherry picked for you. But the really interesting things that happen in the real world are these weird examples. And that's why instructors try to give you weird examples where you encounter something and it doesn't behave like all the simple things you've seen before. It's something a little bit more. That was kind of a tangent, but just remember that as you're taking your other math courses. So, all right, hopefully it seems apparent now that we need a way of understanding what the domain of interest is, and then also associating a domain with a statement, right? For example, if we just say, for any real number x, this is true, that's a false statement because of imaginary numbers. But if we say, for any real numbers, not just numbers, real numbers, then it is true. But if you just say any numbers, it's false. So it's almost like we're kind of hinting at maybe, I'll call this like an observation. Maybe so how do we formalize asking maybe the truth value over all domain elements. I'm running out of room, but hopefully you can see it over all domain elements, right? I was kind of saying that already. With that statement there, I was saying, is it true for all numbers, right? Is it true for all real numbers? It differs based off of the domain that you ask, but it seems like this is this type of question might occur in a lot of different scenarios, right? For example, when writing a program for allowing a student to enroll into a course that has said like requirements like math 1305 is a requirement for a course. right? Like one way of like Boolean checking if the current students in a course are that should be there is asking the question for every student in Math 2305, student has taken with a C or higher Math 1305 or whatever, right? You want to check every single entry in the domain of interest. This notion leads us to quantifiers. Quantifiers are the second aspect of today's lecture. Predicates are kind of easy to understand. They're propositional functions. You have a statement, you plug in a variable, and then it becomes either true or false. Quantifiers are the part that has to deal with the domain and determining whether or not the propositional function is always true over that domain, sometimes true, always false, these types of things. And the first quantifier that we will encounter is called the Universal Quantifier. Okay, so definition. Given P of X, so P of X is just some propositional function that depends on the input variable. So given some propositional function, the universal quantifier is, and I had to pause, I'm running out of room to go erase in a moment. So given P of X, the universal quantifier for P of X is for all, or actually I'll write it in a better way. P of X for all X in the domain. The domain of interest or discord. So this is the universal quantifier. And we have a symbol for it, just like all the other things that we deal with when we're representing quantities or propositions by variables. It helps to introduce notation so that I don't take up all of my blackboard. Or when you're writing your notes, it doesn't take forever to write it. The universal quantifier is written as follows. So the notation for this is the following, like that. By the way, propositional functions are typically denoted with capital letters instead of lowercase letters like propositions. It's a capital P. So that right there is the universal quantifier applied to P of X. And this reads for all X P of X. Okay, so this is a way of quantifying or evaluating a propositional function over an entire domain. Now, this quantifier applied to P of X is only true when P of X is true for every single element in the domain. So when P of X is true for all X in the domain. Okay, and again, that goes back to the way I originally wrote it over here. P of x for all x in the domain, which is saying true for all x in the domain. But you'll very rarely hear me say that. You'll hear me say for all x some condition. And the condition is provided by the propositional function. And as I mentioned earlier, propositional functions consist of a variable and a predicate. The predicate is like the condition. So it's saying for every single x in the domain, is this true? So as an example, maybe we can, well, not maybe, but oftentimes it helps to specify the domain after for all x, put a domain there, and then evaluate the function p of x. So I think a simple example would be, think about this for a second. Going back to the x squared, I'll say like for all x in, and we don't know what sets are, but just think about x belonging to these, one of these items that are about to follow. Okay, so that's the universal quantifier on domain. So x belongs to 1 or 2. So x is either 1 or 2. That's the domain of interest. Universal quantifier applied to this domain, and then that's your propositional function. So is x squared greater than or equal to 0 for every single x in that domain?
Yes.
Yeah, right? 1 squared is greater than or equal to 0. 2 squared is greater than or equal to 0. This is true. Okay. Now, it's true because it's true for every single x in that domain. But if we look at something like for all x in maybe 1, 2, and 3, and then we'll give the propositional function x squared is greater than or equal to 4. Is that true? So universal quantifier applied to variables in that domain. Is this function true always?
No, it's false.
No.
It's false.
Exactly, because it fails at least one point. It fails at x equals to 1. It's false. Okay, now important terminology. So it is false. Good, I'm glad y'all caught that. But this thing right here, the one example of where the universal quantifier is false is called a counterexample. So that right there is a counterexample. Now, there can be multiple, infinite, all kinds of different numbers of counterexamples to a universally quantified statement. However, to show that a universal quantifier applied to a propositional function is false, you only need to provide one counterexample, that's it. Even though there might be infinite many, in this case there's only one, but when the domain of interest is infinite, then you can have cases where there's infinitely many counterexamples. To show that a universal quantifier applied to a function is false, again, you just need to show one counterexample. And in a sense, that's a proof that it's false. So I'll say it one more time. To show that a universal quantifier applied to a propositional function is false, to prove it, you only need to provide one counterexample that makes the thing false. Okay. Now, I think this brings me to the next definition rather nicely, because another way of wording this example right there, another way of wording that would be maybe something like, does there exist an X in this domain that this is false? Is there at least one? Does there exist? That seems like another way of interpreting this quantification on that propositional function. So it might be the case that there's a relationship between universal quantifier being true and universal quantifier not actually being true. There's a relationship between a universal quantifier being false and the existence of a counterexample. The existence. Does there exist one? Right? And that leads me to the next definition. And this is the other quantifier that we will encounter. So again, we're given p of x. The existential quantifier okay. I just keep on like the existential quantifier for p of x is, let's see, the best way to write this would be p of x maybe is p of x for at least one x in the domain. The domain of discourse, the domain of interest, whatever you want to call it. You get the idea. Okay. So this is denoted by another symbol that you need to become familiar with. It's this backwards capital E, like that, like that. And I will always say this and read it as follows. You'll probably, actually I might say this sometimes, but typically when I'm encountering the existential quantifier, I'll say, there exists p of x, or there exists x p of x. That's how I would read that symbol. Now, so this is kind of like, this is related to the universal, but it's somewhat on the other extreme. In order for the universal quantifier to be true over all elements, or universal quantifier applied to a propositional function be true, it has to be true for every single element in the domain of interest for this one. For the existential quantifier to be true, it only has to be true one time. As soon as it's true one time, then it's true. So for example, well, actually I should probably like write that down for you. So there exists x p of x is true whenever p of x is true for at least one x in the domain. Okay. Now, going back to our previous examples here, let's look at maybe like the first one there. There exists x that is in 1, 2, that's set, such that x squared is greater than or equal to 0. So is that existential quantifier on that domain and that propositional function true?
Yes.
Yeah, it's true for all of them, but it's true for at least one, right? So something maybe to note that if the universal quantifier applied to a domain and propositional function is true, then the existential surely is as well. What about the next one? There exists x in this domain of interest such that x squared is greater than or equal to 4. So what about that example there? Is that true or false? The universal quantifier was false, but
True. True.
it's true for at least one of them in there, so that means that the whole statement is true. So, okay, just because, I guess what we're observing is just because the universal quantifier happens to be false doesn't mean that the existential quantifier might be true. But going back to what I was hinting at earlier, there seems to be a relationship between testing if a universal quantifier is false and the existential, right? Like, didn't I say earlier, knowing if this universal quantifier here was false is essentially asking, does there exist an element in the domain that happens to make it false? Like, if that happens, then the universal must be false. Okay, and that leads to a very important point. Now, I just remembered that before I get to that point, as far as like a model in your head of how you should think about these things, so maybe I'll call this like mental model. Is that the universal quantifier applied to P of X is essentially logically equivalent to P of X1 and P of X2 and dot, dot, dot off forever. And this is for every single X in the domain of interest, right? Maybe just to like really illustrate it, I'll do one more P of X3 and dot, dot, dot. So the conjunction operation is only true when, like for example, like P and Q is only true when P is true and Q is true, right? So I'm telling you that you can think of the universal as a conjunction over every single element in the domain of interest for your propositional function. Does that kind of like make sense? Right, like if any one of these are false in this conjunction, the conjunction is going to be false. That's using 2 lectures ago, right? In a similar fashion, the existential quantifier can be thought of as the disjunction over all elements in the domain of interest. And we know that the disjunction is true when at least one of them is true, right? So this is a way of thinking about them, about these quantifiers. We're just kind of exhausting every element in the domain and applying the conjunction or disjunction respectively for universal and existential. Okay, now I say a mental model and not exactly because of a detail that I would feel bad not mentioning. Now, if we had a finite set of elements in the domain, this is exact, perfect. If we had a countably infinite set of elements in the domain, which we'll learn what that is in a few weeks, then this is okay. If the domain of interest is like the set of real numbers, something that is not countable, again, we'll learn what that is, then this is not exact. So I just have to like say that out loud, because if the elements in the domain are not countable, we can't list them out like this. Just a little subtle thing that I don't think a lot of you would have picked up on when we got to that section. Now, what's like, when negating conjunctions and disjunctions, what's one logical identity that like I really wanted you to remember from last class?
Morgan's law?
The Morgan's law. Please, please always remember that. So with that, let's take the negation of the universal and see what happens. So we're like, maybe we're just like curious. So if we negate the universal quantifier, that's the same thing as negating that long list of conjunctions over the domain. Right? I'm telling you that they're basically logically equivalent. So on the right-hand side here, I see the negation of conjunctions. The negation of the conjunction is the
Disjunction of the negation of each proposition.
by De Morgan's, exactly. I'm glad that you said that. So this is going to be logically equivalent to not P evaluated at x1, and then that and is going to become an or, and then not P of x2, and then or not P of x3, so forth and so on, for every single element in the domain. Okay, now it looks like something above it. We have an or applied over every single element in the domain of interest. What other thing that we know about applies the or the disjunction over everything in the domain of interest? Any guesses? Or over everything in the domain. So it looks like we can rewrite this as using the existential quantifier. And we can write it like this. This is there exists X, not P of X. Right? We can, whenever we have an or disjunction taken over the entire domain of interest, we can express that as the existential quantifier. So basically what we just learned is that negating the universal quantifier becomes the existential quantifier of the negations. Okay, So now thinking back to, well, actually, let's kind of argue the next one. Let's argue the next one first. So that's the negation of the universal. What happens when we negate the existential? Well, the existential can be thought of as a bunch of disjunctions between every single element in the domain, right? So this is like negating P of x1 or P of x2 or P of x3 or dot, dot, dot off to every single element in the domain that we evaluate at. Okay. Now, again, we apply De Morgan's law. The negation of the disjunction becomes the conjunction of the negations. So this will become not P of x1 and not P of x2 and not P of x3 and dot, dot, dot off to enumerating everything in the domain of interest. And what do we end up with? We end up with propositional function and propositional function and throughout every single possible choice of elements in the domain, which looks like the universal quantifier, which means that we can rewrite this as a universal quantifier. So for all x not P of x. So the negation of the existential becomes the universal of the negations. And these are consequences of De Morgan's law. So I should probably just say that by De Morgan's laws for logic. Okay. So how does this like relate to what we were talking about earlier? Well, let's just maybe it might not be the best example, but let's just see. Oh no, it will be a good example. So what did I have? One, there's like all x in 1, 2, and 3. X squared is greater than or equal to 4. I don't know if that's exactly what I have, but that's still a valid example to look at. Applying the universal quantifier to that domain and then this propositional function. Now, suppose that we didn't know, right? We didn't know what the truth value of this was, right? Suppose we didn't know what the truth value of this was. Now remember, propositions, including propositional functions, are either true and false as soon as you set a domain of interest. It's with the predicates, in the quantifiers. So suppose we didn't know that this was true. Let's look at the negation and see what happens. Because we can transform the original thing, we negate it, we can look at its opposite truth value. So not all x in here. What is this truth value? Right? Whatever the truth value of this negation is the opposite truth value of the original thing. right? Again, we have this dichotomy between truth values. Well, using this law up here, we can say that this statement here, so everything below, so this one right here is logically equivalent to the existential. So there exists X in this domain such that not P of X, and this is the function. So that's just by applying this rule. Now, we can further simplify. There exists X in here. That's just the domain of interest. Now, here's kind of a thing that might throw you off. We're negating this statement right here. The negation of X squared greater than or equal to 4 should have the complete opposite truth value with no overlap. What's the opposite of X squared is greater than or equal to 4?
4 is greater than X squared.
Yeah. In other words, X is strictly less than 4. Same thing though, you're good. So we can write this as this. X squared is strictly less than 4. So we look at this and we say, oh, there's that one. 1 squared is strictly less than 4. This is true. Which means that this one is false. Because we just found out that the negation of that statement is true. The original statement must be false. Again, there's always this dichotomy between declarative statements. And so sometimes it's easier to take a quantifier and a propositional function and negate it, use De Morgan's laws, and look at the opposite value and determine if the opposite value is true or false. If the opposite value is false, the original is true. If the opposite value is true, the original is false. And it helps when dealing with complicated sequences of declarative statements. And this type of reasoning is actually, I've seen it personally in with former students showing me law entry exams, things like that, where for law school, for whatever reason, well, obviously there's a connection with logic and reasoning, but I didn't know how actually close it was. So whatever the standard law school entrance exam is, one of my former students, I saw him at a coffee shop in San Marcos, and he was studying to go to law school, and he showed me the exam, and literally this type of reasoning is the same exact reasoning in these techniques that they're exactly what were used to formalize the notion of written arguments. So it's super interesting that there's a relation there. But I think now that we've gone over the basic definitions and kind of reasoned through things, that this is a good place to stop the recording for today's lecture. And now I'm going to take some questions from students or take a break.